With respect to videos, have you checked anybody? Is there any difficulty in accessing videos after 21st March? No. What was the last video that is uploaded? Anybody? On my end, I see a lot of them. Some student emailed me that he cannot see the videos after 21st March. Last one is March?
Yeah, last one is 21st March.
Oh, I've been uploading every day. What? Okay, maybe some problem. I'll fix that.
Possibly the playlist, maybe?
No, maybe what happened was I'm closing the browser before it publishes. Maybe that can be the case. But I'll figure it out. Okay, so today we will just briefly discuss monitors again. And then we will go on to a different module, the memory management module. So let's recap with monitors. Now the projector is not good. Okay, we have a problem. The dock cam is, I think it's broken. It's not working. So I'll use the board. So let's do that. Let's use the board. So we said monitors. So monitors are data structures. So these monitors, let's say you declare a monitor. It has a data type This data type can be integer, string, or whatever you choose to have, doesn't matter. Then it has two functions, at least two functions, f1, f2. It can have n, but it should have at least two functions. So these two functions have certain properties. But let's first define them. So they don't return much, just void foo. For one, they can take some arguments, arg1, arg2, right? And then let's say there is another function void foo2 which has some separate set of arguments. So arg3, arg4, right, and so on. So it has n functions, and then it has some parameters called the conditions. So let's say this is condition C1, condition C2, and that is the entire data structure. Right. So this is the entire data structure. Now what is the property of this data structure? The property is that mutual exclusion between functions. So mutual exclusion, by that what I mean is that if let's say there are two threads T1 and T2 and there is a global monitor declared, say M1, right, and they share the same instance of the monitor, then if T1 does M1.F1 and T2 is doing M1.F6, this acts as critical section. Which means that when T1 is executing F1, T2 cannot execute F6. And when T2 is executing F6, T1 cannot execute F1. So whenever a particular thread executes a function of a monitor, it acts like a critical section. That is the first property. The second property, so this does not work for if you have two separate instances. So if now T1 did M1.F3 and T2 does M2.F3, this can work in parallel. You can execute that in parallel. Right? It's the same monitor data type, but different instances. But if you have the same instance, you cannot execute in parallel. So that is what is mutual exclusion. Now there is another property called the condition. Now this condition C1 and C2, these are not numbers, you cannot add them, you cannot use them to compare, or these are not even strings, so that you can read them. These are parameters, and you can only use these parameters to do two things. The first is the weight on a particular condition C1, and the second is a signal on C2 or C1, whichever you choose. Right? Rather, we can say weight on Cx and signal on Cx. Cx can be 1 or 2 in this particular scenario. Now what happens in weight? Now you know that when you have these functions of the same instance of monitor, it's as if thread 1 is in critical section. If thread 1 starts executing F1, then as if thread 1 is in critical section. Or whichever thread starts executing function of a monitor, it finds itself in critical section. That is how monitors are designed. Right? So if that is the case, then what does weight do? The weight on condition Cx, when you call this, you can only call this in some functions of a monitor. Right? Because that is what the thread will execute. So you can call weight in a function, and what will happen when you call weight on a particular condition? The thread that calls weight, so thread that calls weight, no, you cannot see it, so maybe I will write somewhere else. Let's write it here. So yeah, so say weight Cx. So this means that thread that calls weight Cx gives up critical section. So this CS is critical section, that is short form of critical section. So gives up critical section and then blocks. So blocks itself. Now this block is the same block that we did for project 2. That it goes from the ready queue to a separate queue. Right? So this is the same thing. It's not doing input output, it's just a blocking queue. So this is not the same as the wait queue. Wait queue only operates when you are waiting for input output. But this thread is not waiting for input output. This thread is just blocked. So this is a separate queue, which you can call it as blocking queue. Right? So it goes to a blocking queue. Now that is what is the function of wait. Now how will it get unblocked? It can only get unblocked if some other thread calls signal on the same condition on which this first thread was waiting. Right? You cannot call signal on a different condition. You have to call signal on the same condition for which that other thread was waiting. So then what will happen when you call signal X, say some other thread called signal Cx, then any one thread that was waiting on Cx gets unblocked. And when it gets unblocked, then that means this implies it finds itself in critical section, or it gets the critical section. So you have to do signal very carefully. Yes.
So that means you can't have more than one thread only wait on condition.
No, you can have more than one thread. But you have to call signal more than
Okay.
one. Right. So it cannot get the critical section the moment you call signal. It cannot get it. So instead of saying it gets the critical section, we can say it unblocks and competes for critical section. Right? So it cannot immediately get, because the thread that was calling signal, that is in critical section right now, because it is executing the function. Right? So it cannot immediately get it, but it unblocks itself, and then in the next CPU scheduling cycle it will compete for the critical section. Right? So that is wait and signal. Now we will do one example, the producer-consumer problem. We will try to solve it using monitors, and then the other examples, the readers, writers, dining philosophers, will be your homework. Right? If you try to do it, I will ask them in exams, and maybe we will discuss one of them and put the other one in exam. So final exam, not in the module exams. Right. So let's try to solve producer-consumer. So all this has been recorded. So you can take notes, but I won't have written notes for these ones because I'm not writing there. So let's do producer and consumer with monitors. So if you have producer and consumer with monitors, what will you have to do? You have to declare a monitor. So monitor which solves the producer and consumer problem. So let's say monitor M. Now what will be the data type? What can potentially be the data type here? What? Integer what? What for? What? No, so what will I use that integer for? What all data types did we need for producer consumer? We needed in, right? We needed out, and we needed a buffer. All those can go as data type. So in is an integer, then out is also an integer, and buffer is an integer array. Maybe n, however many you want. Right? It can be that. Then you have to have two functions. So what will be the first function? You can say that okay, the first function is producer. Producer, and it takes an item as input, right? Yes.
I'm sorry, what does that line say? Oh, the data type.
Yeah, different data I'm declaring. So integer in, integer out, and integer buffer in. It's an array. Right. So you have to declare. Okay. So now we have to declare these functions. So producer, it maybe takes an item as input, and what does it do? Producer, it just says that okay, so you can initialize it to 0, out as 0, and all buffs are zeros, right? Initialization will be a part of the data type section as well. So then or you can have a separate function, init function. You can have a separate init function in monitor to just initialize. That is a separate issue. So now what the producer will do is the producer will do buff in equals item and will do in equals in plus 1 mod n, right? And what does the consumer do? The consumer doesn't require any consumer takes an empty item as input and then makes item equals buff out and then makes out equals out plus 1 mod n, right? Now will this work? You have mutual exclusion. Producers, if you have multiple producers, they don't produce at the same time. If you have producer and consumer, they are not producing at the same time. And if you have many consumers, they are not consuming at the same time because it's mutual exclusion. But nowhere we say that producer has to wait. Right? We have to say that if the buffer is full, the producer cannot produce. So producer have to wait. So how do we incorporate that? So this one will not work. So what we have to do is we have to modify the functions of the producer. So we have to say that okay, now the code actually becomes very simple. So what we say that if in on oh yeah, we can say if in is equal to n minus 1. No, is less than equal to n minus 1, then do this. Else you wait on producer. So we have to have a condition like this. Here we have to have a condition like this. And then in consumer, what do you do? If in is so if it is not empty, so that means if in is greater than 0, then you can do item equals buff out and then out equals out plus 1 mod n, else you wait on right. Now we have stopped the producer and consumer, but who lets the producer and consumer go? So the consumer should let the producer go and the producer should let the consumer go. So where will they let go? So right after creating the item, producer should let go. So what you should do, that right after this line, you should signal consumer right, and right after this line you should signal producer, and then you have two conditions. So if you haven't written the conditions, so you write the conditions consumer producer, right? So this is the entire data type. But just writing the data type won't work, because you have to use the data type and write the program, right? So how to write the program? So what does the producer do? So let's say this is a producer thread, and this is a consumer thread. So initially you have to declare a monitor M, let's say M1. So this is an instance M1 of the monitor. So you have to do that is a global instance. It is shared by both the threads. So then what do producers do? Producer do in a while one loop M1 dot produce. So maybe item, it gets some item equals X, produce item in a while loop, and consumers do while one item equals, or maybe you can have a output, doesn't matter. No, just consumer or M1 dot consume, no, consumer item. So this is the whole solution. You should not write part of the solution. This is the whole solution to the producer consumer problem. So you first declare a monitor data structure with the appropriate functions, and then you write the code using that monitor data structure. So whenever I tell you to write solution using monitors, these are the two parts you have to write. First is declare the data structure, and then use the data structure to write the code. If you don't do either, then it's a problem. So do you understand? Yes.
So the producer function, like you're checking if n is less than or equal to n minus 1, isn't that always true? Because you always do n equals n plus 1 mod n. So it's always.
Yeah, so the condition figure, I just wrote the condition.
Yeah.
So basically just if the buffer is full, figure out a way to find whether the buffer is full or not. Yes.
And that takes care of the case if the consumer's trying to read something from the buffer from the socket of the buffer that's not being written.
Yeah, but so this takes care of that. That is not been written to.
Okay.
This line, because it only increments. So these conditions I just wrote, but these conditions is you can figure it out that if the buffer is full or buffer is empty or not. So update these conditions, these ones. But these are not as important. So now try to solve reader writer and also the other one, dining philosopher. Okay. So let's now move on to module number 4. I would have really liked to have the doccam, but don't know why it is not working. So while we are discussing the initial concepts of memory management, let me restart the system and see if the doccam works. That's it. Anyways, we have to use this one. Okay. So let's start our discussion on memory management. So before we do that, let's recap a little bit. So when we said that we want to run a program, and we said that in order to run a program we need to give it memory. So can anybody tell me what all things need memory? What all things will need memory if I want to run a program? So what are the different parts of a program that needs memory?
File,
What?
the file,
Which file?
the program file.
The program file is in hard disk, right? The code that you write in high level, that doesn't need memory because you cannot execute it. It's just a file. Yes. Yes, what gets allocated? Variable, not names. What?
The variables themselves.
The variables themselves. So, what different types of variables are there? There are two broad classes of variables, right? Static and where this we have discussed very early, like maybe in the second or third class. If you don't remember this, then it's my failure. So you have to. So we have to do this recap. What? There are 4 different parts of a program that should get memory. So what are the 4? You have to tell me.
Stack.
What?
Stack.
No, this is stack is not a part of it. Well, okay, stack. Stack is 1.
Yeah, if you didn't say stack, all our previous classes.
What?
I said if you didn't say stack, all
No, stack is there for a purpose. But yeah, that's fine. Stack. Then the code. Yes. The code. Global data.
And then the heap, right?
Yes. So these are the 4 things. Global data, code, stack, heap. Now what is the purpose of stack? Local variables, not only local variables, addresses, and then registers. One of the earliest recitation classes, if you go, we discuss in detail what goes in stack. Then what goes in heap? Yes.
Whatever is new allocated.
And newly allocated, and there is another qualifier, you can give it another qualifier. Newly allocated, and that is variable in size. Right? You can change, yes, dynamic variables. Variables that are dynamically allocated. So all these things need memory, right? All these things need memory. Now, before even giving it memory and before even running a program, do you know how much memory you need for global data? Is there possibility to know? You can just count the bits that are declared as global, right? If 2 integers are declared as global, you need at least 8 bytes, right? So this is known, and this is known. Is this subject to change? Can it change during program execution? it cannot change. So this is known and does not change. What about code? Do you know how much memory you need for code before even executing it? You know, right? Now, there are certain techniques that if you apply them on code, then you may not know. For example, you may choose to, let's say you wrote a code, right? You wrote a big software code, and for maybe 10 users to log into a system. And you wrote a huge code that develops the login interface for 10 users. Now the thing is, you know that this system will not have a new user or will not have a new administrator, let's say you know. So the code, but you still wrote the code to add a new administrator. So that code which adds a new administrator will be executed very few times over the lifetime of that software. It will be maybe executed once or twice in 6 years. So when you are executing that login interface, you may choose to not load that particular code which adds an administrator. Right. But now if you, let's say after 5 years you decided to add an administrator into the system, then you have to run that code. Right. So if you have to run that code, you have to load it. So in that case, the memory required for code might change. But those are rare cases. So if you just follow the principle that you have to load the entire code whenever you execute, then code memory is first of all known and second of all doesn't change. Right? So it is same. Code is also known and it does not change. How about these? Stack. How much memory do you need for stack? Do you know beforehand? You don't. Why? What does it depend on? Why don't you know? You just look at the functions and they will tell you how many local variables you need. You can just read the functions and figure out. Yes.
But stack frames are also stored on the stack, and those you don't know how many times the function's going to be.
Exactly. Yes. So that's a good response. So stack does not just only store local variables. They store a lot of other things. Now even if a stack only stored local variables, what will happen is that if you call multiple iterations of the same function, let's say you are doing recursive functions. Right? If you do recursive function, you are calling multiple iterations of the same function, but with different inputs. Each of those iterations have their separate frames, function frames. So, while you are executing a code, you don't know how many times you are going to call a particular function, depends upon the input. Right? For different inputs, you might call the same function different number of times. So, you don't know how many frames you need to keep in the stack. So, stack size will vary depending upon what input you are giving to a particular code. Right? So this stack size is not known initially and can vary. How about the heap? Can heap vary?
No.
Why not?
It's dynamically allocated.
So can it vary? If it is dynamically allocated. So look at the code. Let's look at this code. For I equals 0, I less than j, I plus plus. Let's say this is the function foo and it takes int j as input, right? And it has int I equals 10. Int I equals 0. So in a foo it is doing this, and then it is saying that okay, int q equals malloc size of int, and then finally it can or may not do free, right? So now this, what is it doing? In a for loop, it is just allocating Q, right? Multiple instances of Q it is allocating. Now if it does that, and the for loop, the number of times the for loop goes depends upon the input. So you don't know how many times the memory will be allocated. So those are some examples. So heap also is not known, and can vary. Right? So now there are a lot of things here. So first of all, code and global data you know, and they are not valid. So you can immediately allocate memory for it. Right? You can for these two, you know exactly how much. This is known, but this is not known. So how do you even know how much memory is needed for a program? You don't know. So what you do is, what is done typically is that for the known things, you know how much to give, and for the not known things, assume maybe 4 MB. Just an assumption, right? So that is how we know how much memory is needed for a code. So by combining exactly known memory plus some assumptions, we know that this is the total memory requirement. We know that. Now just knowing the total memory requirement will not do it. You also have to give that memory, allocate that memory to a program. So this whole chapter of memory management discusses this thing. It discusses how to allocate memory, not only to a single process, but to a large number of processes at the same time. Right? And it also discusses what if you don't have that amount of memory. What if you want to run 10 programs and the cumulative memory requirement of 10 programs is much more than what your memory can support? What do you do? Right? So it also discusses that. So let's go into more detail. Let's start with a very simple idea of giving memory. It is a contiguous memory allocation. So what is contiguous memory allocation? Let's look at that. Yeah, I think it's a contiguous memory allocation. So let's say this is our RAM. Right. Let's say this is our RAM. A portion of it is reserved for the operating system. You cannot write on it. Right? So let's say this portion, the upper portion is reserved for the operating system. The rest can be used by programs. Now, in order to allocate memory, let's say you have allocated memory. How do you know, or what will you do, or which registers will you access in order to know where my program starts and where it ends? How will you know? Base and bound. So this means that if I want a program P0, if I want to allocate it, let's say this program P0 this is the amount of memory that it needs, X amount of memory. Right? So if I want to allocate this to this RAM, then what I need are two things. We need a base register or base value and a bound value such that base plus bound is somewhere here. So this is base plus bound. Now how do you get the bound? Bound is basically global data plus code plus 4 MB. What is this? This is tag and hit, but some assumption because you don't really know how much. Right? That's just an assumption. What if you need more? If you need more, you have to extend the bound. How do you extend bound? System call. So you have to ask the OS. So they give me more. If the OS decides yes, then you get more. Right? So that is how it works. So what you do? Okay, you have this bound. Now let's say this means that this will be x amount. Then you have another program P1 0 to y. The P1 can start at, let's say this base value was q, right? So this will be q plus x. So P1 can start with q plus x plus 1 and then end at q plus x plus 1 plus y. No, not 1 plus 1, just q plus x plus y. Okay. Then if you have a P4 or P2, P2 which is maybe 0 to z, right? Then what will happen? P3, so this is P1's memory, P0's memory, this is P1's, this is P1's memory, and if P2 is z, then P2 will start from q plus x plus y plus 1 and maybe end here q plus x plus y plus z. P2's memory. So this is contiguous memory. What? Q is the base value, the first base value of P0. So from 0 to Q, it is OS memory. You can't write on it. So that is contiguous memory. Now the thing is we don't use it. Yes. So you have to tell me why.
If you ever need to extend, you hit the program. If you ever need to extend a memory, you hit the program below it.
Now that answer nobody gave me, but that is a good answer. And nobody gave me before. But that is a good one. Hold on to that. But there is an easier answer. The easier answer is, let's consider this scenario that you have 10 MB. Right? You have 10 MB. Let's say 20 MB. Let's say you have 20 MB RAM. Nobody has that, but let's say you have 20 MB RAM. So 20 MB RAM means actually you can write on it. It does not include the OS memory. So you can write on 20 MB RAM. Right? So you can have programs. So let's say this is our 20 MB RAM. And let's for now omit the OS part. Right? We are not worried about OS. Now this is our 20 MB RAM. Now let's say you have a program P1 which needs 5 MB. And you have a program P2 which needs 6 MB. And you have a program P3 which needs 10 MB. If that is the case, can you run all three together? No. So if you can't run all three together, let's say you choose to run P1 and P2 first, right? So P1 goes here, P1, this is 5 MB, then P2 goes somewhere here, this is 6 MB, so 5 plus 6, so all this, which is 9 MB, this is free memory. You can put anything into it, but you cannot now. There is a process waiting. There is also free memory. There is a process waiting. You cannot use it. This is called external fragmentation. Process P3 is waiting. There is free memory 9 MB, you cannot use it. So that is called external fragmentation. Bad for memory because it reduces memory utilization. You cannot use it. There is another form of external fragmentation. What is the other form? Let's consider another scenario. So you have that same 20 MB, right? You have that same 20 MB, and now you have, so this is our 20 MB RAM. Let's say there is a process P0 which takes 5 MB. Then a process P1 which takes 6 MB. And then there is a process P3 which takes 2 MB. Right? It takes 2 MB. Fine. So how will you allocate? First of all, will all be allocated? Can you allocate all the processes? Yes, the summation is less. So let's say you allocate P1 here, this is 5 MB, and you allocate P2 6 MB, and then you allocate P3 which is 2 MB. Very well and good. This becomes 8 MB. There is no external fragmentation. There is free memory, but there are no processes waiting. So right now there is no external fragmentation. But now let's assume that there is another process P4 that comes after P3. P4. And P4 is, there is a mistake here. This is not 6 MB, this is 11 MB. Okay? And this is 13 MB. So now let's say P4 comes here, and P4 is a process that is 8 MB. P4 is an 8 MB process. Can you allocate it now? You cannot. Why? Because this is 7 MB and this is free. 7 MB wasted. Now let's say P2 finishes. If P2 finishes, then this implies this is free. So this is how much? 6 MB? 6 MB free you have. This is also free. So how much total memory is free? 13 MB. 13 MB free memory, which is greater than P4's 8 MB. Can you execute P4? Yes? No. You need to shift, but contiguous memory allocation doesn't say that you can shift. So here again P4 waits, but you cannot. You cannot execute it. Then you have enough memory for P4 to execute. That is another form of external strategy. Yes. So then you can execute. If P3 finishes, you can execute. But P3 doesn't finish, P2 finish. That is another form of external strategy. Yes. I mean, contiguous memory is used in certain systems, but we'll talk about that